So, good evening and welcome to Fundamentals of Micro and Nanofabrication, Week 8. The course instructor is Professor Susavan Avasti and Professor Sankar Selvaraja from IISc Bangalore. I am Vikas Pandey from IIT Jodhpur, the teaching assistant. This is a brief about me, the classroom meet link, YouTube channel, and my contact details. So, in continuation with the lithography, we will continue the part 3 of the optical lithography and we'll discuss a bit about e-beam lithography. So before starting, if you have any specific questions, you can ask or we can discuss even at a later stage. Any questions? Okay, so let's move forward. So we have seen that we were discussing about mask a lot uh, about mask in case of optical lithography, whether it was proximity, whether it was contact, or whether it was projection lithography. In all these cases, we were talking about mask. And I was saying that mask is the physical pattern. Like the pattern we want, it is a kind of physical form of the pattern we want. In case of projection lithography, we can scale it up or down. Okay. So what are the key function of mask in lithography? It is a template which is used to project circuit patterns onto the wafer without causing any damage. So this is a critical thing, that this should actually not, this mask itself should not be such that it causes some damage to our structure or wafers. Okay. In case of projection and contact includes proximity lithography. The mask serves as the template for transferring patterns. What are the type of regions on mask? So on a mask, if you see, I will show you some mask. I have a video of it. Okay. So there are two regions. One is transparent region, which will allow the light to pass through it, and opaque regions that will block light to define structures on the wafer. And whether the structure we want is on it on the transparent region or on the opaque region, that will define the type of mask. We'll even discuss about it. So what are key features for a good mask? First one is it should be defect free. That is, it should have no particle, no cracks, or no transparency issue. The transparent region should actually be transparent. It should not happen that there is some uh, residue, some unclean part, or maybe some crack or some scratches which are actually obstructing the light. Such things should not be there. The second and very important thing is which makes the mask. Ideally, if you say it is glass only, good quality glass. But what is so unique about this glass is that it it has very nice smoothness, no roughness, like because any roughness that will be on the mask will also be transferred to the pattern. That is why this has to be very smooth, and that is why this mask, the glass coated with chromium or titanium, as per our requirement, this costs a lot, and in fact, it is quite surprising that even this small template for mask, like the basic material for mask, we are not getting in India. That we have to import. That quality we are not producing in India. That smoothness, that surface low surface roughness, and that uh, uniformity throughout the mask, that we have to maintain. Then second is the design and the alignment structure. So design files like GDS, OA, SIS, these are some common you see design formats. Like for a movie we have MKV or MP4. For a what you say, for a image we have JPG, PNG. For design files, they are GDS or OSs. Okay, and they are prepared using EDA tools. There is one more format, CIF, okay, which are commonly used to prepare these mask designs. And they are prepared using EDA tools. Some of the EDA tools that I am familiar with is LEdit, and that is from Tanner Tools. Then I think Clavin is one very common tool. Such tools are there which are used to create these patterns. Plus, we have learned about alignment structures in the previous class. So mask will include the alignment structure to ensure proper alignment between multiple layers. For at the edge of this uh, mask, we have scribe lines for measurement that are used to define our measurement parameters, critical dimensions, so that what we do is that we cannot check each and every after making this we cannot check each and every circuit or each and every part, so we make some critical dimensions at the edge, and if that has been reproduced perfectly or as per the requirement, then we say that it is fine. It like we will get what we wanted. So these scribe lines are used with critical to understand whether our critical dimensions has been reproduced or not properly on the wafer. Alignment structure, we saw crosses and boxes. This helps align different layers during wafer processing. Okay, so we have seen how this mask is used to fabricate to do lithography, but how this mask itself is produced, and that process also is very similar to a lithography process. The mask fabrication process is very similar to lithography process, but here we don't have a fixed mask but instead we have a software based file which have these patterns defined. So we start with a blank mask. And what is a blank mask? This is a glass or quartz coated with chromium. So we have very fine, smooth glass that has been coated with chromium, uniform coating. And then on top of it, photoresist is coated. When we go for buying this commercially, we will get two type of such blank mask. One just with glass and chromium or quartz and chromium, and the second type which has the photoresist pre-coated on it. So the both the types, but the ones which has photoresist pre-coated on it, it have lower shelf life, although it is very well coated, that is not very easy to replicate in lab environment. It is like industry standard and everything coated, so that is a better one. But the problem with this, when we have this combination, then we have something that have lower shelf life. Or we can coat the photoresist just like we coat for our wafers. And how do we coat a photoresist on wafer? Anyone? What is the process? Yes, anyone?
Any deposition process. Sorry, what is the question again, please? Sorry.
How do we coat a photoresist onto our wafers? Spin coating.
Spin coating.
Yeah,
Yes.
we can certainly coat it using some other techniques also. Nowadays, some better techniques are being developed, but the most common one is uh, the spin coating, because it is easy to coat, and we know that by varying the speed of coating, speed of rotation after pouring the PR, we can define the thickness of our PR. Then, instead of using a mask to make the mask, what we do is that we expose the resist with LED, laser, or electron beam lithography. In case we need very good precision, we generally go for electron beam. Okay, and we will be covering electron beam lithography in uh, the next section in today's lecture only. Okay, so here the exposure is somewhat, you say that, suppose that we start with this blank sheet which has photoresist coated, and then using a laser, let's assume we have a laser that is pointed, and it will expose pointwise, so this point like that. And now the regular, and where the points where, suppose that it has to make something like this, although, yeah, so it will just leave this part and it will expose all other parts point by point. Okay, so this is software controlled, and if you see this process, it will be very slow, sequential. Okay, then we develop the regist and perform the chrome etching, very similar to what we do in case of our normal photolithography. Then we strip the regist, clean, and characterize the mask. How we characterize? We check it in microscope, and we check the thickness, like uniformity, everything is fine or not. Each and every critical dimensions, we will check that whether it has been perfectly made on our wafer or not. Critical dimensions means the portions where there are chances that some overlapping can happen, or some if like some two structures might merge because they were too close. So those are the critical dimensions that, generally, if we go for like making the mask, if suppose that I give, uh, for printing of my mask, that is to get it exposed, so I will give them some critical areas that I think that they have very low dimensions. Those are very thin lines and they might get erased if they had not been done properly. So these dimensions I will give. And after making this, we will check that those areas have been perfectly made or not using microscope. Okay, and we will check the dimensions where the dimensions that we wanted, they are same or not. Are they varying, or is the variation is in tolerance, like is it 1%, 2%, plus minus, then it's fine. But if it is 10, 20%, and that, then we have to make it again. Okay, and if necessary, then we will go for repairing the defect, clean, and recharacterize. So what the whole process that is done by the mask shop, like the place where this mask will be made. So if you are not making the mask, if you are just making the design and you are sending the design to someone to make the mask, that process is called as tape out. Okay, sending the mask design to the mask shop for fabrication. So it's not that, if you are dealing with lithography, you will be making everything on your own. Sometimes it happens, sometimes, or most of the times, it happens that mask making facilities are at limited places. So it is not necessary that we make the mask, but we must understand how this mask is made and what are the critical things that we have to consider while making the mask. Okay. Any questions still here?
Just one question.
Yeah.
Uh, Strip resist, like how can you please explain?
Stripping the regist means removing the regist after everything is done. And stripping in it generally, like when we buy a photoresist, we must understand that a photoresist will always come in combination of two more liquids. Okay, we generally buy, or we have PR plus developer plus stripper. Okay, PR is our photoresist, clear. Developer is the chemical that we put it into develop, and stripper is the one, if we put that liquid on the PR, it will remove each and everything, like whatever is there whatever PR is left, that will be removed.
Okay, so non-developed PR, right?
Yeah, non-developed PR also, and even if it was developed or whatever it was, stripper is simply a liquid to remove the PR. And in general, in our labs, we are using acetone as a stripper. But in some cases, you might need specific stripper for your PR.
Okay, in the process, let's say I add, we add photoresist, we add developer. Now we want to remove because we detected that there is some error
Yeah,
in the. So how do we make sure that you know whether we remove everything
we
or we.
remove everything.
Okay, okay,
We just dip in and remove. But in this case, it is after, like we have put PR, we have developed, pattern made, then we etch the extra chrome. We are now like we have our mask ready, but we have an extra layer of PR over it. And we don't want this PR because PR is not that smooth, or it will actually stick to our wafer in later stages. So we remove the PR. Once its work has been done, we have to remove it, and that is done using strip. Fine,
yes, 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 fine, thank you.
got it. Okay.
Yes.
Yeah. Any other questions?
Sir, hello.
Yeah.
Sir, the time is like normally developers so this much seconds and all we are keeping it. That how we are like what parameter anything like just
See, it depends on two things. One is the thickness. Okay, because one and the most important thing is the thickness of the PR. The same PR with different thickness will take different time to develop, and there are some standard curves. Like when we buy for any electronic component, what we see is that we see a data sheet, right? Whenever you are going to buy any electronic component, we check datasheet, what are its parameter. Similar to that, when we buy a PR, we get a datasheet associated with, like suppose that I am going to buy SU8 or say S1813. Okay, so these are numbers. Just like electronic components, there are specific numbers, model numbers, or specific you say chemical numbers given to these PRs, and they have comprehensive data set along with that. So if you see those data sets, like if you just search say micro composite S1813 data set, you will find good data sets, and it have the whole parameters for how much rotation, uh, how much speed you will get with what thickness, for which what thickness, what will be the development time, what are the specific developer, like if you are using some one kind of developer, it might develop in say 50 seconds. For another kind of like there are 2 3 developer that can work for this one single PR. Okay, so in that case it will depend on uh, what kind of developer you are using and what is the thickness. Same developer, same resist, but if you have a thickness of say 1 micron and say 2 micron, it will be different. Fine. So the time depends on type of developer we are using as well as the thickness of the resist. Fine.
okay, sir.
Yeah. Yeah. So there, what are the type of these masks? Okay. One is binary mask. That is simple binary, like 0 and 1, opaque and transparent. Okay, standard mask with transparent and opaque region. Second one is phase shift mask. Like we discussed in one of the classes, that to counter this problem of diffraction and all, phase shifting is done. One region, another region have different phases. Okay, the light will be phase shifted so that we get good resolution. So one area that will allow the light as it is, the adjacent area that will shift the phase by lambda by 4 and these things, not lambda by 4, pi by 2. Okay. Then another transparent area. So such grades are there. This is used to improve some resolution. Then there are some reflective masks. Okay. So instead of this transmission, this reflective mask, these are generally used in extreme UV, where deep UV, we know UV rays, then we go into deep UV range. Then there are extreme UV lithography also. These rely on reflection instead of transmission because they can actually not be transmitted normally. So there are regions that will be reflective. Here we are saying opaque and transparent. There will be like transparent regions and reflective regions that will reflect back the UV. Okay. Then there are two type of mask field types. That is bright field mask and dark field mask. Bright field mask means if you see the mask, if there is nothing to be made out of it, it will be transparent. Simply a bright field mask. And the patterns will be small opaque regions. So here opaque patterns on transparent mask. This is a bright field mask. Then comes dark field mask, where transparent patterns on opaque mask. So here the whole, in case of dark field mask, the whole mask will be opaque. Only the regions that we want to make, that will be etched out, or that will be a transparent region. Now comes pellicle. Pellicle is a protective layer added to the mask that prevents dust and particle from adhering to it. This is important because it prevents contamination from being transferred to wafer. So it is kind of a dust reflective part. So without pellicle, the dust will actually, like, it will get charged since it is glass. Okay, and dust particle will adhere to it. So this is a coating that actually keeps dust a bit away. So so that we get less number of contamination in our imaging. So there are some, these are the normal masks. Okay. There are some advanced mask making techniques also, like phase shift mask we talked about, that improves resolution by using phase shift alternate to each other. Embedded attenuation phase shift mask, again, to further improve it. Then reflective mask, that for extreme UV. Okay. Then there is one more thing, that is electron beam lithography for mask. Okay. When we have to make sub-micron or nanometer features, okay, we cannot rely on photolithography at that time. So we have to make, although this mask will be used for photolithography, but we want better precision. And since we know that the electron's wavelength is much less compared to light, even if we compare it with UV. So we can go for electron beam lithography for making masks, since it will give us better precision. Then there is something called as exposure latitude. This is the measure of patterning quality involving both illumination and resist process. Okay. So we have discussed about dose. Okay, so what are the key factors that define this exposure latitude? This first one is the dose that will define the that will have some effect on line width after resist patterning, and then some tolerance or robustness to change in this exposure dose and thickness variation. So it is not that suppose that I was saying that in the previous classes. So suppose we want 90 millijoule per centimeter square as our dose, but there can be some variation. Say when we started exposing the first half second, we had a lower intensity, and the say when it was closing or it was going down, that time small spike also occurred in between. So we might be getting something like 80 millijoule per centimeter square, or say 98 millijoule. So such changes, as well as when we are coating the photoresist. Suppose that we wanted 1 micron thickness, but the thickness varied. In some regions, it, it was say 1.2. In some region, it becomes 0.95 micron. Okay. So sorry. So such variations should be compensated, and that is defined by the exposure latitude. This is a parameter that you will find in case of uh, any photoresist and its data sheet also. So, so if you see the data sheet of any photoresist, you will find this exposure latitude, in which on the x-axis we will have the exposure dose, and on y-axis we will have the critical dimension. When this exposure latitude is higher, okay, we will get stable critical dimension over some variation of doses. So that means although there is one optimal dose, but some variations, like it will cover some variations. And if it is like that, like some changes in dose as well as some changes in uh, this photoresist thickness can be considered, like that is fine, it will still work. Then we say that it is more robust. Okay, the process is robust compared to someone which has some process which has very critical, this window is very small. Okay, then there is boson curve, like again curve which will have contour kind of patterns. Okay, this also you'll find in the data sets. Uh, like when we optimize the process, we make these things. Okay, so we have seen depth of focus, that is the focus tolerant of optical system during exposure. Okay, it will depend on wafer position and focal plane. So if this is the wafer, and ideally the projection system should focus on the wafer itself. But suppose that the focusing point is at some distance, say at, if I am taking this at 0, down is plus and above is minus, so say minus 0.5 micron, and at some places going even below it as 0.45 micrometer. So this range, okay, this is the focusing range of our optical system. So this Bossing curve explain like shows the relation of variation of this critical dimension, that is what dimensions will be imaged on the photoresist with respect to changes in exposure dose as well as focus. So the focus variation, say depth of focus is, we talked about depth of focus, that is the area which will still give the critical dimension, that if the focus, there is defocusing of this much of distance, still we will get our perfect image, or the critical dimension will still be imaged. That is depth of focus. Okay, so Boson curve takes into account variation of critical, not account, sorry, it shows the variation of critical dimension with change in exposure dose as well as focus, combination of these. So this help, like when you are starting the process, you will be able to define the process window for our acceptable critical dose variation, critical dimension variation. This is important to understand the acceptable range of both exposure. What will be the acceptable range of exposure dose? How much variations we can go? Like we say in any process, there will be plus minus. Say 5% variation is acceptable, or 2% variation is acceptable. So based on that, we will go for process. And what will be the variation in focus within which we will still get our critical dimension. Say the same machine, same process, everything, but in one case, if you have a critical dimension of say 20 micron, okay, then the same process will work fine. But suppose that we have the critical dimension of 5 nanometer, then a lot of things will change, because in that case, small variation of exposure dose might not give us the same thing that we want. Okay, so we have to take care of all these things. Fine. Any questions still here?
No questions. Thank you.
Okay. Then there is something as linearity and proximity. We make a mask and we want that it must be linearly mapped, in the sense whatever is the dimension, whatever is the size, it should be one-to-one mapping in case of contact and proximity lithography, and in case of projection lithography, one-to-one mapping with a relation of whatever we want, say by 5x or divide by 5, whatever is there, we should get exact one-to-one. Then it will be a linear relationship, and which is important to ensure accuracy across various feature size. It should not be that if we have any 20 micron features, we get 20 microns. But if we have, say, 400 micron features, we get 350 only. And if we are having 1 micron size features, we are getting, say, 1.5 micron. So it will not be a linear one. A linear one will be for 20, 20. For 400, it should give 400. For 1, it should give 1 micron. So generally, it cannot be linear for infinitely all the dimensions. It will have a range in which it will be linear, and we generally want our process and all other things to have that, like we optimize it to have maximum linearity. Then there is one other thing. We saw that there will be interference from light sources, due to which sometimes it might be that when we are taking the features separately, they are getting linearly mapped. But when we have the same features present along with other features, like the neighboring features, then that will not be linearly mapped, or not be linearly uh, linearly imaged, or not be having the same dimension as expected. So that also defines that will define the distance between the features, and this will also depend on the wavelength of the light that we are going to use. So it is not just that what size of the what dimensions we are making, but the distance between the dimensions, distance between features also plays an important role, and that also comes under the critical dimensions. It is not just that we have, say, three electrodes to be made. It's fine. These are when we are making this, not just the size of electrodes, but the distance between them is also important, because if there are changes in the distance between them, that will also affect our output. So what is this proximity effect that we talked about? One is line end shortening. That is, the printed line is shorter than the mask design. So on the mask, the line was like this, but we got on the wafer is shorter line. Okay. Corner rounding. This is one of the most common undesirable effect where the corners will get rounded. So we made a sharp feature, but we got a rounded output. Okay. This is mostly due to resolution. So if we have very dense features, that will lead to non-uniform critical dimensions due to proximity. How to use this? How to like compensate this? Then we can go for assistive features, like we can go for some proximity correction that we can so that we can ensure better image fidelity or better image replication. Okay. So what are these optical proximity corrections? How do we correct this? Since if we have dense features on our mask and we want it to be perfectly replicated on our wafer, how do and due to this proximity effect and due to the limitation of our wavelength, it might not be getting properly replicated. So how do we tackle this problem? So this is this whole tackling is under optical proximity correction. So these are techniques used to address proximity effects by adding some assistive features or additional features to the mask itself. So helps correct line end shortening and corner rounding. So these are two common problems that occur. So we have to take care of this. So how it is done? So we take the layout from the design and then we do DRC. DRC, whenever we are giving our uh, design for printing, it is not that it is directly printed or directly made on the mask. First, design rule checks will be done so that it is actually manufacturable or not. Then we will do some in the design, some optical proximity corrections will be done. And then the mask will be fabricated using that optical proximity correction. How it is done, we will see. Okay. And this improves the resolution and accuracy of the printed patterns. So how this resolution is enhanced? Okay. So there are some techniques. Okay. Yeah. Yeah. So optical proximity, this will be covered in this design layout adjustments. Okay. So we saw that we have this optical lithography or photolithography system. We have to now improve it or enhance it so that we get better resolution. So how what are the areas that we can focus to improve? The first one is illumination system or the light source, where we can change the wavelength of the light source. So to go for a lower resolution, like better resolution, Should we increase the wavelength or decrease the wavelength? Yes, anyone?
Decrease the wavelength.
Decrease the wavelength. Why? What is the relation?
Resolution is inversely proportional to lambda.
Yeah. So Na upon lambda. Is it correct?
Yes, I think 2 is there. Some.
Yeah, 2Na upon lambda.
Ah.
2 or sometimes K, 2K Na upon lambda is used. Then second is using projection system. We have seen that using projection system, we can have bigger mask. So we make a mask with liberty and then we reduce its size or scale it down using projection system. Then some processing technology we can use. We can even do some improvement in mask technology, or we can do some design layout adjustment so that we are able to reach to such smaller dimensions of sub 10 nanometer technology nodes. Okay, so first way is wavelength reduction. Since we so since we know that resolution R is proportional to lambda upon Na, it's not Na upon lambda. So will the resolution increase by increasing lambda or decrease by increasing lambda now?
Resolution, it will increase by increasing lambda. So, and
Yeah,
more resolution is better.
no, less resolution is better, not more. This is when we are telling about, okay, yeah, sorry. Yeah, we are talking about, there we are talking about this critical dimension, right?
Yes,
Yeah, here
this
it
is
is
critical
resolution. Yeah,
dimension.
so it's opposite. Yeah, so resolution will increase with, no, it's the same, na? Lambda upon Na. Lower resolution is better. Higher resolution is not better. If we have a resolution of 2 nanometer and
Hmm.
if we have a resolution of 5 nanometer, which one is better?
2 nanometer is better, but I think means it is my understanding. I can be wrong. We say 2 nanometer is more resolution than 5 nanometer.
Yeah, that is when we talk in terms of comparison, right? But when we are talking about resolution, that is the minimum feature size that we can replicate. So lower resolution is better.
Correct.
Lower
So
resolution is better, not a higher resolution. And resolution is directly proportional to lambda. So smaller wavelength will give lower resolution, and lower resolution is better.
okay. Concept wise, I'm okay. Like no
Concept
problem.
wise, yeah,
Huh.
but the thing is that when speaking, we have to take care that resolution is not what we understand. Resolution is more about the smaller dimension, and smaller the resolution, better will be the output.
Correct.
Yeah. So now G line and I line is used for micron scale features. We saw that at G and I line mercury lamps and like argon ferrite lamps were used. Okay, so these were for the micron scale features. Now, nowadays, deep UV, that is 249 nanometer wavelength is used that allows sub 100 nanometer features. Then we have shifted now to 193 nanometer. Not everywhere, but we are talking about the current technology in case of generally processor technology and these things. Along with 193 nanometer, immersion lithography is used, in which the whole system is passed through like light, not light, some liquid, okay, and that actually improves the resolution. Now, extreme UV is being tried, which is 13.5 nanometer wavelength, and this is future for sub 10 nanometer features. Okay, But when we are shifting this, then there is a problem that the same photoresist will not work. The lens system has to be able to take like tackle such a small wavelength. Okay, and such the optics have to support shorter wavelength, because any small aberration or any small uh, imperfections will affect these wavelengths a lot. Okay, so these are some of the challenges when we are going for wavelength reduction. Then second is light source engineering. That is, conventionally we had circular light source. Okay, now to improve the resolution, there can be things like ring-like shape, four-pole configuration, and two-pole light source. And what they does is that they tailor the diffraction pattern. Like diffraction is a problem for us, but sometimes it can even be used to our advantage. So we saw that it actually helps us in projection system, a bit of diffraction. Similarly, using the understanding the diffraction, we can employ the combination of these light sources such that the diffraction pattern gets cancelled out and we get improved image contrast and reduce the stray light. Okay. When we have on-axis or perpendicular light source, we may miss high diffraction orders. When we have off-axis, that is tilted patterns, like these are the light source going perpendicular to our patterns or the mask. Okay, then we might miss the high diffraction orders. Whereas if we have off axis, that is, there is some tilt in the diffraction pattern, that will, like, if we have the light source at some angle, then we will have this higher order diffraction, like happening after plus 2, minus 2, minus 3, plus 3. These order of diffraction beams that will come into image plane, and that will sometimes even lead to improved resolution, because we will be able to go to orders lesser than the actual wavelength. So such light sources can even be modified, that will help in our resolution. Then if we talk about mask, we saw that the basic one is binary mask, opaque and transparent. But this has some problems, like when we have dense patterns in this, they can cause interference and lead to blurred features. So phase shift mask, that is phase shift of pi between adjacent features. So one feature, the light will not interfere with the another feature of the adjacent, like light of one feature will not interfere with adjacent feature, and thus there will be proper contrast, there will be proper shift, like it is something like they will not interfere if we have light of opposing intensities. Okay, so phase shifted intensities at adjacent areas, that will not interfere, that will lead to better contrast. And how this is achieved? This is achieved by modifying the thickness or the refractive index of the mask. So we will not have a uniform thickness throughout the mask. One point, like at one place, thick, less thick, thick, less thick, like adjacent patterns. Like you see in case of some window glasses also, these kind of patterns are nowadays used to like to reduce the diffraction that is coming from the sunlight and these things. Okay, so There can be two type of phase shift mask. One is where we have no chrome. It is only based on the phase shifts. These patterns are made. The contrast is due to phase shifts only. Then is attenuated phase shift mask, that is partially transparent or absorbing layer. Okay, so instead of using opaque chrome areas, there will be some areas which will absorb layer. So in this case, it is like areas where we want it to be opaque. We are designing it such that the light does not pass through. And then the areas that we want to be transparent, we are designing it to be allowing the light. And that we are doing using the thickness, modulating the thickness as well as the refractive index. Okay. Then another technique is immersion lithography, where we increase the nimmer. We saw that there are two things, lambda and Na. These are like these increase our these affect our resolution. So one is wavelength we are playing with. Second one is we can change the numerical aperture. Higher numerical aperture will give us lower resolution since it is inversely proportional, but it requires immersion fluid, some like water or oil between the lens and wafer. So we have mask, wafer, and in between we are filling it with some kind of liquid having a higher refractive index that will increase the effective numerical aperture beyond 1. Okay, so normally it is air. Instead of air, we are putting liquid like say water or oil based on our uses. This is generally being used for 193 nanometer immersion lithography, that is improving its resolution further. But it has a problem that we have to handle this uh, fluid, okay, as well as like we already know that handling the wafer and mask itself is a cumbersome thing. Now we have to put a liquid, and that also in a very thin area. The whole setup might have to be uh, kept inside the liquid. In such cases, handling is a problem, as well as it can even sometimes, since we are putting something in contact instead of air, like it might bring some contamination. Although it is like very pure, cleaned, everything, it might create some contamination or defects. Then there is something called as double and multiple patterning. So instead of having masks such that they are very dense and they are suffering from interference and this thing, diffraction, if it is too dense to be taken care by simple methods, we can separate this into two different masks. Okay, so we can make these patterns in two sequences instead of one. Okay, so we'll get the higher resolution without them interfering with each other. If they are at some dense, like if there is some dense pattern, then it was causing the problem. Now half of the density, if you are putting in one mask, half in another mask, so it will become much less dense and it will have no neighborhood effect. Okay, so we can increase the pattern density without changing the light source or numerical aperture. So this is one simple solution, but it will increase the number of steps. Again, alignment and these problems will be there. Then is spacer double patterning. So what is done is that it uses some spacers on the side walls of a sacrificial pattern so that we will make new pattern. So it is not that we are doing it double, like whole process we are not repeating twice, but it might be that we are making some patterns like this and we are putting some sacrificial layer, some extra layer like that. And we know that in this area, in the second, using the second mask, we will do the patterning, like some extra part we are putting that has to be actually patterned in the second layer. So once we do this, this will be left and that will be patterned using the second or the double mask. And as such, we will get the combination of these two. Sometimes even if it is event ends, we can go for triple patterning, but it is like it will be the complexity becomes even more than this if we are go for triple patterning. So the problem is in all these cases alignment accuracy and the cost will increase significantly. As I said, one of the most important and one of the most crucial and costliest part of this fabrication process is lithography. And that is why if we are doing it multiple times, that will increase the cost significantly. So now we have seen it. Yeah, any question?
Yeah, one doubt, please again.
Yeah, yeah.
Spacer. Where do we add that spacer? Can you please?
Like one way is you are making a pattern. Suppose that you deposited gold. Okay.
Hmm?
You patterned it using half of the patterns. Then again you have to pattern like you cover it with something and like you kept the PR intact and all, and then you again made other like if you want to make other patterns again, you will again have to deposit gold to make those patterns because everything else has been removed. So instead of doing it like this, it can be done like in the first pattern we keep some extra part, like we made half of the patterns and we kept other some the other patterns that we want, we kept some gold in that area instead of clearing it, and that will be cleaned or that will be patterned in the next level of lithography. Are you getting or wait, I will not getting properly?
Like double patterning. Understood. Like
Yeah,
दो बार pattern करना है,
yeah,
right? Spacer is some sacrificial. It was written.
yeah. Sacrifices, that means you see, suppose that we have to make patterns like this, very dense. Okay,
Hmm.
but instead of this, we are doing two patterns. So first we make a pattern, box kind of pattern. Okay. And in the second case, what we did is that we made a pattern just to remove these two parts. So in the first lithography, what we made was not the intended one. There was some extra part that was still kept, that was sacrificed in the later, like second stage lithography or double pattern.
Okay. Okay. Understood. Understood.
Understood, no? Yes. So now we have seen the photolithography whole process. Okay.
Right, right. So just again, sorry. Then
Yeah, yeah.
here, second, whatever we do, the second step, na, that should be of the higher cost material, and the earlier should be because we will sacrifice that in the
No,
second step.
anyway, like this whole process, if you see, na, it is very, very least cost effective process. You are depositing whatever may be the cost, you are depositing that in the whole area, and then you are removing it.
Correct, correct.
Okay, so here, yes, you can say that cost content constant, but here both of these layers are patterning the same material, not two different materials.
Okay, okay,
Same
okay.
material. It is the same material. That is how we are improving the pattern resolution. That the same material, instead of doing lithography once, we are going for lithography twice, so that if there was like the patterns were too dense to be resolved, so we are doing this same process twice. So again, the consideration is that if we have the cost of material is high, so it will become double because we are putting the same material two times now.
Correct, correct.
So that is certainly a consideration. So now these are video from one of lectures. I found it very good from Duke University, in which some basic how this photolithography works. Okay, some clips I have taken from there. Okay, so is it okay? Are you able to see this video? Yeah.
Yes,
So
yes.
yeah. So see how this whole process is there. So if it is a photo mask that have a pattern, okay, and below is a wafer, okay, there is a metal pattern. So this is a mask, okay, and then we want we are putting the light over it, and it is getting imaged. Here also you see some kind of diffraction is there, okay, but this shows the basic principle how this lithography happens, okay. So what is the whole process of a simple photolithography system? First is we prepare the substrate, that is we clean or we deposit whatever we have to deposit. Second stage is we apply the photoresist. This include soft baking. We apply the photoresist using spin coat plus soft bake. Then we expose the photoresist to light like we saw. Then we develop the photoresist, etch out the substrate, and then we remove the photoresist. And this is stripping where I was okay, etching. So we can say one the process in simple terms is spin coating followed by exposure to light, then after exposure develop, then after develop etching, and after etching stripping. This is the general process of a photolithography, right? So if we see the mask, okay, this is one mask that you can see, simple glass with the patterns designed using chrome over them. If you see through a microscope, you are able to see these videos, right?
Yes, yes, we can see.
Okay, so this is a simple mask. And how these masks are designed? They are designed using EDA tools. Like you can see, this person is designing where you will put the patterns in the software and all, and then this will be written over our mask. And this, when the starting material will be this glass coated with complete chromium. And now it has, once it has been made, we have just these patterns left. Other parts has been removed. So can you tell, is this a bright field mask or a dark field mask? Anyone? Yes. Anyone? We talked
Uh,
about two. Yeah. Ajit.
no, sorry, but like I know you explained bright field and dark field mask both earlier,
Yeah. Yeah.
but I forgot that. Sorry.
Yeah. So bright field is simply, you can say that, to remember, uh, just keep in mind that we are playing with light here. Okay.
Okay.
So bright field is in which light will be in more area. Dark field is where light will be in the less area. So when we are talking about bright field, field means the background. The
Hmm.
background is transparent. So in this case, most of the background is transparent. So it will be a bright field
Bright
mask.
field mask. Correct.
Yeah.
Okay.
And if we had everything dark and just the points where we want the pattern open, that would have been a dark field mask. Right?
Okay.
Seeing this, you will remember better. That's why I kept these videos, and like taking the video of this lithography room is very difficult. So I referred this some of the videos that were available over internet, because taking the video in a yellow room, that might destroy our samples. That is why I preferred this. Okay.
Yes, yes. These are useful. Thank you.
Okay. So next is a photoresist. Yes, Aditi, you
Sir,
were saying.
sir, this one designed using laser, like a mask will be normally people laser writer using or like this
See, for a normal case, it will be laser written. Okay, laser based. Like in our like at IIT Jodhpur also we have a laser writer facility. Okay, so with that, but if you are going for some smaller dimensions, then we go for e-beam or such a deep UV lithography to do to make that. Got it?
so like multiple mask and all we have to use for UV lithography, sir, or we can for single mask also we can use.
Uh,
You-
in case of mask making, it is done sequentially, one by one.
Okay, sir.
Yeah, because it is software based. It is not mask like hardware mask based.
Okay, okay.
So whatever number you use, the time will still remain same for one single mask, because it is to be done sequentially using a software.
Okay, okay.
Yeah. So next is, we talked about photoresist, right?
Sir,
So
one more that soft
yeah,
baking we are using, sir. Soft baking what purpose, sir? I forgot,
I
sir.
will show you.
Okay,
Okay.
okay.
So the basic principle of using the photoresist is like, we have a wafer, we put photoresist over it, and we spin over it, and it deposits uniformly. Now, if we see it practically, a coating will be there, and if you cut it, you will see that on the wafer, some thickness of photoresist will be there. And we had talked about positive and negative photoresist, right? Positive will, uh, like the area that will get exposed to this light will get removed. In case of negative, the opposite. Now, when we are coating this photoresist, it is a liquid, right? But this liquid is spread over our wafer by spinning it at a speed, but it has to dry. The resin that is inside it, we talked about the components of this resist, okay? That has resin, then sensitizer, these things. So, just, yeah. So to harden it, not harden in the sense, just to dry it, we do soft lithography, soft bake. That is, after spin coating it, we heat it for a very small time at a, say, lower temperature. What it does is that it dries the resist, and we get a some kind of solid structure. Otherwise, it will be sticky. Okay. So next comes the light exposure, and the light exposure system is somewhat like this. Okay, and all these, if you see the real pictures, you will see that they are in a yellow room. Okay, so once we have coated it, soft baked it, then we bring it to this alignment and exposure system. We have the mask fit in it wafer that will come in close contact, and then we put the UV light over it. Okay, then next is development. How we develop? Taking this out, doing a hard bake that will harden it further, like the rest part that is left that will get hardened. We put in developer. So first solution that we had was PR. Second solvent is developer. Here we are putting it in developer. And so what the developer did was it removed. Yeah, now you see how it is actually being done is that once developed, this is a wafer that is dried. Once this whole thing is done, it has to be rinsed with water. It is not just that we put it in developer, take it out, and done. We have to DI rinse and then dry it. Okay. So what the developer did was it dissolved the area that we don't want. And now we have the pattern of photoresist over our wafer. But still the thing that we want, that whole metal, say we deposited gold, we want to pattern the gold, not the photoresist. So next is you remove that by using etching method that will be covered in the next like next week. Okay. So let's see this complete one. Okay. So we start with such wafer, clean wafer. Then in this case, gold is deposited, and then after patterning, some patterns, patterning and etching, we have some patterns of gold made. Other areas of gold has been removed. Are you able to see this video? Like everyone?
Uh, yes, yes.
Okay.
Now the black screen is there, right?
Yeah, now it's completed. So
Correct.
now you saw the difference between all these three. One, we had clean wafer. So if we start with a clean shiny wafer. We coated it with some material of interest. Then we did lithography over it. And after lithography, we only have the pattern of the material we coated. Other parts are clean. Okay, this is a simple process of lithography. Okay, so if we see the complete lithography process, it is done in a yellow room. Since the light has the role to play, no white light is done, only like faint yellow light is there, so that the materials don't get exposed to light before we want. Okay, so it starts like this, that in the yellow room, you see. Yeah, so this is the wafer that has already been coated. Okay, like already been coated using material, say gold. Okay, now on this, spin coating of the photoresist has to be done. So this is a spin coater. It has vacuum chuck which will hold it using vacuum. Okay, so that whole wafer is kept over it. Properly aligned. Vacuum suction will on. It will just get stick to it. And recipes are fixed. Like say, if they are going for some uh, thickness, that is fixed at what speed it will give what thickness. So they are taking that, like they are putting those parameters, then taking the photoresist and pouring it over the wafer, completely covering it. And then this is adequate enough to cover the whole area, and then it is rotated. And once rotated, you will see a thin layer remains. Everything else is thrown out. And it is like it is rotated for some time. Okay. Once done, the vacuum chuck is switched off, taken out, and then it is baked. This is where soft baking is done. You were asking about soft bake, right? So this is for some time we are soft baking, that is hardening it, like drying it, then taking this mask, loading it into the system. So this only this is the pattern that we want it over this wafer. Now this wafer will also be loaded just below the mask. Again, here vacuum systems are there, so they will hold it. So now you see this wafer is going close to the mask, so it will just be close to it, and that system will come and it gives the light. So now the process that we saw there, here the light is falling only in the areas that are transparent. The part that was not that was opaque, that is not getting exposed since it is in very close proximity. Taking it out, if we do a developing, so this is the developer solution, pouring it, and then we will put this wafer inside it. And you will see that in sometimes the whole pattern will appear. Just shake it. All other areas dissolve, only the pattern that was to be there will come. It has to be dried, cleaned and dried, and you see the patterns have emerged. But still gold is there, the complete gold is there. And then it is checked that whether the patterns are there or not. Okay. So this is the whole process of photolithography. Simply after this, the other processes that we will etch out the gold and then we will put it in the stripping solution. Fine. Any like now the things are clear about photolithography, everyone. Hello, am I audible? Yes, anyone? Can anyone respond?
Yes, sir. Audible, sir. Yes, sir.
Audible. So any confusion, any part that you are not able to understand? Anyone?
Yes.
Yeah, any questions?
No questions till now.
Okay, so after developing, there is a hard baking also, so that now the pattern that we have made, that has to be hardened, so that because that whole thing is going to be put into some kind of etchants and all, and it should not get affected by those. So like why we choose a specific resist, once we get into this, there are a lot of other considerations also, that it should be such that this resist should not get affected by the etchant that we are going to use. Sometimes it happens that not sometimes, in general, it is such that directly gold cannot be coated over silicon. Okay, so generally chromium or titanium is used below it, or we have seen actually that Ti is coated, then aluminum is coated, and these things. So in the metallization part. Okay, so sometimes it happens that this photoresist is fine for gold etchant. It is not getting affected by gold etchant, but it will get affected by chromium etchant. But in that case, it is sometimes such that gold itself acts as a mask afterwards, because gold is not affected by the chromium etchant. So all such considerations are to be taken in consideration when we are dealing with this. So next comes when we are talking about resolution.
Sir, one more. Hello.
Yeah,
Sir. I didn't Sir, mask will be normally prepared with the chromium, sir. Chromium mask, sir.
yes.
If you prepare with gold masks, what happens, sir? Like, we can
Why to waste
costly.
why
Money.
to waste so much of money over it?
Yeah, yeah, yeah.
Because its work is
Better.
just to stop light.
Okay, okay, sir.
Yeah,
Okay.
and gold, if you see the gold thickness, more thickness of gold will be required to make a mask, because the reflectivity of a chromium mask is better than gold.
Okay. Thank you.
Yeah. So when we are talking about lithography, we talked about the limitation that in case of photolithography, where we are using light, it is limited by lambda, that is the wavelength of light. So we can go to something below it, which has lower wavelength than light. And that brings us to electron beam lithography, which uses photons. Like in case of optical lithography, we are using photons. And in case of e-beam lithography, we are using electrons. This is not a common method, and you should not go if you are making bigger patterns. Like you saw in the case I showed you, the patterns were actually visible with naked eyes. We don't need electron beam lithography for such methods. Even the simplest photolithography system, that is 365 nanometer resolution system, 365 nanometer wavelength system, that gives resolution of say 600 nanometer. So anything above 1 or 2 micron is fine using optical lithography. Even in case of deep UV lithography and these things, we can go something of 100 nanometer. But if you are going for very small feature size, say in 1, 2 nanometer, 5 nanometer, 10 nanometer, then EB, uh, E-beam lithography, electron beam lithography can be a better option. Here, the tolerance is like the what do you say, the difference of the actual one we like the mask and the pattern. Here it will be a software based mask anyway. That will be less, since the wavelength is much smaller compared to photons. The resolution is much higher. The chances of errors are lesser. Okay, so why to go for electron beam? One is smaller wavelength than light, so high resolution. And when we are dealing with sub 10 nanometer features, so in normal bigger feature size, it's fine. But when we are discussing or when we are trying to make some features of less than 10 nanometer, then we have to go for electron beam lithography. It is a direct writing instead of mask. It is a maskless lithography, very similar to laser writer and this kind of material, where it is software controlled instead of using a physical mask. Since making a physical mask that stops electrons is very difficult, like stops electrons in some part and allows in some part, a physical mask is quite difficult to be made. So it is a maskless lithography. Key advantage of this system is it has a smaller spot size for fine feature definition. We can like what is the wavelength range? Like what is the size of the electron? Anyone? In what range? It's in the range of picometers, right? So the wavelength associated is also in range of picometers. So the the spot size can be very fine if we are, although it will not be a single electron fine, but even if we are talking about 2 3 electron, 10 electron spot size, it is still very fine compared to the size we are talking about in nanometer. The second thing is there is no mask requirement, so we are quite flexible with the pattern. It is not like the optical lithography where we have made a fixed pattern and we are supposed to use that only. To make some modification, we have to physically make the mask again. Here, there is some flexibility since it is a direct write lithography and it has high precision due to electron interaction with the resist. So if we compare this technology, if we are dealing with optical or photolithography, that is in the range of UV of 193 nanometer, the energy that we get from it is around 5 electron volt. If we are doing the lithography, X-ray lithography is also there in between optical and electron electron beam lithography. So that has a wavelength less than 1 nanometer. So feature size we will get say 2 to 10 nanometer or something. The energy is in kilo electron volt. Again, very high compared to 5 electron volt. But when we are talking about electrons, the wavelength is very small, smaller than 1 nanometer, say 0.02 nanometer, and the energy is very high, 20 to 100 kilo electron volt. So with very high energy and good precision, we are able to deal with our photoresist. So what are the component of a electron beam system? It is generally, anyone is familiar with FESM, field effect scanning electron microscopy. The system is very similar to FESM, and in fact, at in most of the cases, FESM and these are a common system. The FESM is modified for electron beam lithography only. So it has electron gun, that is an electron source. The illumination system, that is to condense this whole electron to some spot size. It is not uh, physical optics, it is actually field optics. That is why effect scanning electron microscopy. Okay, so it is controlled using electric field. Then second is pattern generator, where how the pattern will be generated, at what place has to strike, at what place it don't have to strike. The electron beams have to be rastered, have to be vectorized. These things are controlled using pattern generator. They are very similar to old TV system, where we had X and Y controls, and this light, like the light that was coming from the back of the TV lamp that used to travel in a rastering manner, and that was controlled using these field patterns. Then electron optics, that focuses and directs the beam. If we compare it with an optical system, optical lithography, optical lithography using projection optics and mask. Whereas in case of EBL, there is no mask and use an electron optics to write the patterns. Okay. So what are the different sources of electrons that can be used? We talked about sources of photon or sources of light in case of photolithography. In case of EBL or electron beam lithography, we will talk about the source of electron. So it can be of two types: thermionic emission based, which will have heat, that is like tungsten is used, that will be heated to emit the electrons, and then the rest part will be similar. Second case is field emission, which is in case of FESM, where high electric field is used to extract the electrons. Here heat is used, and here electric field is used. What are the properties that we look for when we are talking about the electronic source? One is the brightness. What is the brightness of this source? That is amount of current per unit solid angle steradian. Uh, like because here we are dealing with 3D angles, not just in one direction, but the whole 3D angle we are dealing with. Second is spot size. That is how sharp we are getting the beam. It should not be that it is dispersing in all the direction and we have to put a lot of optics to deal with this diffraction only. Then is what is the spread of electron energy, because it again affects the focus, because we want that the electron energy should be almost in the same range, say 20, 21, 19, 18, like that. It should not be that one of the some part have 100 kiloelectron volt, some part have 5 kiloelectron volt. Such differences should be less, because we in that case will not be able to focus properly. But one big problem with this is, and which increases the cost, is vacuum requirement. We have seen vacuum systems in case of physical vapor deposition also, where when we have to deal with vacuum systems, there are different type of pumps and all, and here we are dealing with very with good, like high vacuum, 10 to the power minus 6 to 10 to the power minus 12 torr. Okay, because we don't want the electron to scatter. And there, when we are talking about sputtering and all, we are talking about a distance of say 5-10 centimeters. Here the distance can be as high as 10-20 centimeters from the source to the target, and that's why we need good vacuum, so that there is least scattering and we are able to focus properly. Then there are two type of electron beam optics. One is magnetic lenses, other is electrostatic lenses. In case of magnetic lenses, we have magnetic field, which will actually lead to less distortion than the electrostatic lenses. Whereas there are some other uh, lens type like electrostatic lens, which have electric field that will focus and that will make it move in different direction. But it is although it is simpler, but it is less effective than the magnetic system for high precision. So for high precision, we can go for magnetic lenses, and for good source, thermal compared to thermonic source, field effect field effect sources are better, because there no heat is involved. Then comes the beam deflector. Again, here it will deflect x y direction. Beam deflector will be used. It can again be electrostatic or magnetic. That will define at what precise locations on the substrate this electron beam has to focus or have to hit. Okay.
So, are you able to hear me? Yes. Am I audible?
Yes,
Yes,
yes.
Okay.
sir, yes.
Then is there are apertures. Again, when we are talking about apertures, they will not be like optical apertures. Okay, they are again magnetic or electrostatic based, that will control the size and shape of the beam. So it is kind of focusing mechanism. Uh, like what will be the size of this beam? What will be the focus size over the substrate? That is controlled using the apertures. So what are the factor when we are why we are shifting to electron beam lithography? Because of resolution. So what are the key factors that determine the resolution in this case? One is the spot size, and this is in turn affected by source diameter and the aberration of our system. And when we talk about aberration, there are spherical and chromatic aberration. Spherical means problem with focusing. That spherical aberration will lead to will be due to imperfection in our focusing optics. Whereas if we are talking about chromatic aberration, this is due to the energy spread of the source. And this diffraction limit is another factor that is due to the beam aperture size. What is the aperture size of the beam? That will again determine the resolution. How do we improve? Like suppose whatever resolution you are getting in your EBL, if you want to improve it, how we do it? We do by higher accelerating voltage that reduces the chromatic aberration, because then the variation of this energy will be less. Everyone get all the electrons will get adequate power, uh, like to have almost similar energy levels, as well as if the beam size, the spot size is reduced, that it is finely focused, that will also improve resolution. But in that case, as you can see that if the beam size is larger, like if this is the substrate and we have beam size scanning this area, and if we reduce it, now the time taking to scan this will be much larger, so throughput will be less, right? It will take more time to scan the whole area. So at the cost of time, we can improve the resolution. So what are the aberrations that we see in case of EBL? One is geometric, one is non-geometric aberrations. Geometric aberrations means, eh, by the name itself, you can understand geometric means where the uh, geometry or the shape is disturbed. One is spherical aberration. The cause can be focal length difference across the electron beam. So focal length can be different for different point on the wafer. Field curvature, so curved focal plane. So the plane, uh, because that has to move at different points. So ideally it should be that if this is the electron source, different optics, so the focus point should be here, 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 like at the surface of all the of the wafer. Whereas it might happen that the focus point is somewhat distributed like this at different points, because the optics will also have some role, or it might be having a small downward orientation. Such can also lead to non-uniform focusing. Astigmatism, that is uh, yeah, astigmatism, that is electron beam elongates in one direction. So ideally the spot should be circular, but what if it is like this, or what it is if it is like this? Okay, in such cases there can be astigmatism, that is vertical and horizontal directions will mix up. Coma and distortion, that is due to the optical imperfection, that is the focusing and these things, the optics, that magnetic or electrostatic optics, that those are not perfect. They can lead to some distortion or optic imperfection in image quality. Second is non-geometric aberrations. That is, the first reason can be chromatic dispersion. That is variation in the electron energy. Chromatic means uh, color, or you can say chroma means color. So that is based on mostly contrast variation and these things. Okay, so contrast variation as well as problem with your source. Okay, so these aberrations can result due to electronic energy variation. So even though every optics is perfectly fine, but we have, if the energy variation is too much, like 20 electron volt to 1 electron volt, such huge differences is there, they can lead to different focal length differences, because one electron will be hitting with different energy, other with different energy, and we will not be able to focus properly at the point, because here the focusing is based on the electronic energy instead of the path length. It is uh, based on this how much energy it carries, that's electric field and these things. That is why the focusing will be different. Second is diffraction, that is beam will spread through the edges. Again, that will lead to non-geometric aberrations. Okay, these I will put, yeah. So these you can see in details, I'll put here. Okay. Then what are the scanning techniques that how it is written on the substrate in the EBL? So there are, one is raster scanning, that is beam scans the entire area. Like if this is the substrate, it will start from here point by point like this, then again second line, third line, fourth line like this, and so on till end. This is raster scanning. The electron beam is moved. It is just that using some optics, we are blanking the area where we want the pattern to be. Just that. The beam is coming continuously in a rastering fashion. It is just that it is being blanked using some optics. Second is vector scanning, where the beam is switched on and off at the specific points. So it will be switched on for these points. For these points where the pattern don't have to be written, at that point it will be switched off. Then again from here it will be switched on. In such cases, the the pattern is more uh, efficiently produced even for complex situations. But the optics is again the optics is complex. Okay, and that is why this will be more, you say, more costlier as well as more complex to operate compared to the raster scanning. But here we will get better patterns, because here selectively it is only exposing the area that we want. No, no blanking is there. So it is like at that point there no light comes at all. Like no electron comes at all. Then there can be some line scan and area scan. It is like the this one has to be patterned. So two type of patterning can be there: line by line, even in case the whole complete wafer, or patch by patch. In one patch, pattern made, then second patch, again the scanning has been is same but small patch wise scanning. Small, the whole area is first divided into patches, then in lines. That is area scan, and one is line scan. Line scan is good for fine features, low energy, and closely packed spots, because in case of area scan, the area that is between these small patches of area can have some imperfections. Area scan is good for large features, high energy, and broader areas. Resist is again in case of e-beam resist, the resist will be a bit different than the photoresist, where the resist will change solubility upon electron exposure. Here, important thing is that it will be very thin since we have to deal with resolution. What is the sensitivity that will be considered, and the chemical nature of the resist. Some common e-beam resist is PMMA, HSQ, MAN. Again, it has both positive and negative type of photoresist. The problem with such photoresist, e-beam photoresist, is the charging effect on dielectric substrate. Like if you are doing it on a glass substrate, it is not conductive, so electron will accumulate over it. It will get charged. It will not, if it is conductive, it's fine. It will conduct from the below because it will have some electrode in it. But if it is accumulating over it, that is problem. Okay. So one solution is to use some conductive layer like thin metal or conducting polymer. Whatever pattern we have to make, if it is in on a non-conductive thing, then we will put coat a small thin conductive film and ground it or connect it to the anode, and then that will minimize the charging. Resolution limiting factor we have already seen. Proximity effect, it again have the same proximity effects. Stitching error, like I said, when we are scanning areas, then stitching these areas one by one is a problem, and that can be solved using moving the stage instead of the beam. This minimizes the deflection and allows continuous large area writing, but it is more effective for millimeter scale features, and it uses laser interferometry for high accuracy movements. Okay. Yeah. Do you have time? Can we continue for some more time? 5-10 minutes?
Uh, yes, so, sometime it is okay. Yes.
Yeah, because this is the last topic. We cover it. Anyway, we are delayed by the starting, right? So, what is the limitation of single beam writing? That is low throughput due to the writing speed. Since we have to put spot by spot. Second is time consuming for large area or repetitive pattern. If we have the same pattern being made throughout the wafer, but we are doing it one at a time. So that is a problem. So what is a solution for this? This is replace the pencil beam, that is the focused beam, with predefined shape, say rectangles. So it is like projection lithography for one small rectangular area. Then again projection lithography for one area. So it will improve the throughput. We are, instead of putting spot sizes, we are making it rectangular or circular according to our pattern. Mostly rectangular is the best one to improve the throughput, and that will make it stepper like. Second option is multi-beam writing, where thousands of beams with different deflectors, and parallelly we are exposing one area using uh, different electron beams. That will increase the field area because in that case one big area is exposed at once, then another area, and here better control is also there. That is just like TV LEDs. Nowadays we have OLEDs and this specific areas where we want the patterns can be switched off. If those areas can be controlled using like if we have a multiple array of electron beams coming, we can like we can switch off those parts where we don't want the where we want the patterns, and other areas we can switch on, and as such we will have one large area being exposed at once. This is currently in R&D, and it might be implemented in next generation CMOS. Apart from this, there are some other alternate techniques which we have uh, discussed somewhere. That is, sometimes photolithography is not good for us, but electron beam lithography is also not the ideal solution. We need something in between. So there are some methods like extreme UV lithography, where UV lithography along with this immersion lithography is used. Nano imprint lithography, where AFM, atomic force microscopy tips, they are dipped into the chemical that we want to coat, and then it is patterned. Scanning probe lithography and other approaches like X-ray lithography and dip pen lithography are used. I have put all these in details here. You can go through it. Anything that you are not able to understand, you can ask in the next class. And some problems along with questions are also there. Mostly it is theoretical kind of questions this week. So you can discuss, like if you are not able to understand any part, you can ask in the class. So any questions still here or anything in your mind that you'd like to discuss? Anyone?
No, thank you for the class today, Vikas.
Yeah, Hari, you have some questions?
Sir, small dot in our research labs, we can design CMOS inverter, sir. Like CMOS inverter, we can design, sir. What are the facilities which are available in our research labs in IITs and all? We
Yes,
can
yes, you
design
can.
CMOS inverter with this facilities.
Yes, just the problem is that we
More
might not,
masks.
no, mask everything we can make. The problem is that we might not be able to go to feature size of say 10 nanometer everywhere. There are very limited facilities for that. Even throughout the world, it has very limited. We have very limited facilities to go for such sub nanometer technologies and all. Okay, but say if you want to design something in the range of say microns, that is
Micrometer
fine.
range.
Yeah, yeah,
Micrometer range and all we can design,
yeah,
sir.
yeah. Easily we can design. Even in our lab, we are designing these things. It's fine. We are making transistors and all. So if you are making transistor, you can make CMOS or whatever you want.
Okay, sir. Okay.
So next topic is wet etching, which will be covered in the next class. As I was saying that
Sir,
wet.
is classes are sufficient, sir, for writing? I'm not listening NPTELs and all.
No,
Is it
no.
sufficient, sir?
You should see those things also. We are just
Okay.
like we are putting things from our perspective also, so that you get some insights. But sir is covering things in lot of details. Like you see, even this 2 hours is not sufficient to cover so much. Like this field is too vast to be covered in such small duration. We are. I am just presenting a summary, and you see, 2 hours is less for it.
Like time. Okay, okay. And they explains too much theory, sir. Like more. So very difficult to understand some of the things and
Although, like, I could have gone for this directly going for questions. That is what we are expected mostly. But the thing is that it has a lot of contents, right? So directly going for questions will not cover all the parts that
so at least can you provide their PPTs, sir? Like
all
your PPTs are different and their whatever they're explaining PPTs are different, right? Same PPT, sir. Whatever you're explaining. like
No,
and
sir's PPT is not with me. Like that you can get.
can you I sent a mail, but there is no reply from them, sir.
I think that
Can
is
you?
already available as a transcript
And
and
they're giving only notes they're giving, sir. Whatever that's they saying, sir.
but
Like
in the notes, you will see
the
the slide pictures are there.
slides, sir, but the resolution is very poor, sir. Some of the things unable to see and all.
That you will have to write to sir only. Yeah.
So that is like I sent a mail also, but there
Yeah.
is no reply from them. But to 23rd, the meeting with them, sir, with the
Yeah. You can.
faculty,
Yeah.
I will ask
Yeah. You
because
can
I
ask.
understand, but the little bit, but every time I can't see that one, right? So if PPT means I can understand little bit and
Yeah.
all.
These
So
PPT
that
I am putting. So you are able to
yeah, yeah,
access.
PPT, but those are different. But the questions I
Yeah.
think they we will get it from the exam.
Yeah.
We are getting from
The
their.
questions that I am putting is from some previous versions of this course only. Okay, so
Okay.
you might like these questions are made from by sir and his team only. Okay, so you might get
Okay,
similar
sir, but
questions.
yes, yes, but yeah, but their PPT is there means it is very easy to before the exam to
Yeah,
can see and according the topics I can read from the textbooks and all it is easy.
and
I seen sir that lecture notes the resolutions are very poor
very
because they're
less.
taking the screenshots,
Yeah,
unable to see the lines and all.
you
So
will have
if
to
one,
ask sir for that.
I sent a mail, but there is no reply from them.
Yeah, in the live
From
interaction
your
also.
side, if you can possible, you have more access with those people, IIT Madras people. If you can help it us, it is very helpful, sir.
Yeah, okay, I will try.
Please, at
Anyway, you
least.
you can raise this in this in the live
Okay, I'll
interactive
try it. Yes, and
segment.
23rd I will ask,
Yeah.
sir.
Okay. Any other
Thank you.
questions or anything?
Yes. Sir. No. So
So
after we are teaching, what is that one? Sir? Sensor designs, right? After etching and all,
yeah,
sensor designs. Sir.
the etching and one more topic, then I think sensor design is there.
Fine, sir. Okay,
Okay.
sir. Next week
So
we'll meet you. Sir.
yeah,
Thanks.
that's all. See you all in the next week. Thank you.
Thank you very much, Vikas, for the lecture.